Welcome back to SpaceInfo. Today we are going to talk more into detail about our home planet, Earth. Earth is the third planet from the Sun. As you may know, has one natural satellite, the Moon. Earth's moon is larger than that of any other satellite, apart from the moon of Pluto. Usually satellites are much smaller than their parent planets. A lot of characteristics make our planet unique. One of the most important is free liquid water on the surface. This is possible only because the temperature is above the freezing point and below the boiling point of water, accompanied with an atmosphere which is thick enough and composed by the very right mix of gases needed for life to exist. The diameter of the Earth is 12,000 kilometers. At the center, there is an iron-nickel core where the temperature is 5,000 K, which is almost 5,000 degrees Celsius, which are about 9,000 degrees Fahrenheit. The pressure is 300 million pascals and the density 12,000 kilograms per cubed meter. As a comparative measure, the pressure of the atmosphere at sea level is about 100,000 pascals, so that pressure is about 1 million times bigger. Also, the mean density for the whole planet is around 5,520 kilograms per cubed meter. Below the surface, the core is divided into two layers, inner and outer core. The inner core, below 5,150 kilometers, comprises only of 1.7% of the mass of the Earth. It is solid because of high pressure. The outer core is molten. Also, the solid inner core rotates with respect to the outer core and mantle. Earth's lithosphere, which constitutes the hard and rigid outer vertical layer of the Earth, includes the crust and the uppermost mantle. The lithosphere is underlain by the asthenosphere, which is the weaker, hotter, and deeper part of the upper mantle. The lithosphere-asthenosphere boundary is defined by a difference in response to stress. The lithosphere remains rigid for very long periods of geologic time in which it deforms elastically and through brittle failure, while the asthenosphere deforms viscously and accommodates strain through plastic deformation. At the end of the Precambrian era, about 700 million years ago, more than half of the continents were together, forming the continent known as Gondwana, containing Africa, South America, Australia, and Antarctica. About 350 million years ago, Gondwana was on the South Pole, but it moved toward the equator before the final breakup. Mutual collisions formed new mountains, and finally, in the beginning of the Mesozoic era, about 200 million years ago, all the continents were joined into one supercontinent, Pangaea. Quite soon the flow pattern in the mantle changed and the Pangaea broke up. The Atlantic Ocean is still growing and new material is flowing up at the mid-Atlantic ridge. North America is drifting away from Europe at the rate of a few centimeters per year, the growing rate of a fingernail. At the same time, parts of the Pacific Oceanic Plate are disappearing below other plates. When an oceanic crust is pushed below a continental crust, a zone of active volcanoes is created. The earthquakes in the subduction zones can even originate 600 kilometers below the surface. In the mid-ocean ridges, the depth is only tens of kilometers. As the solid part of our planet, also the atmosphere was very different from the modern one. There was no oxygen. The presence of oxygen became being consistent and enough only when the first organic chemical processes started in the oceans more than 2 billion years ago. The original carbon dioxide is now mainly concentrated in carbonate rocks, such as limestone, and the methane was dissociated by solar UV radiation. Today, the main atmospheric components are nitrogen and oxygen. Other gases, such as argon, carbon dioxide, and water vapor are present in minor amounts. In particular, 78% is nitrogen, 21% oxygen, 0.9% argon, and 0.1% other gases. Trace amounts of carbon dioxide, methane, water vapor, and neon are some of the other gases that make up the remaining 0.1%. In general, air pressure and density decrease with altitude in the atmosphere. However, the temperature has a more complicated profile with altitude, and may remain relatively constant or even increase with altitude in some regions. Because the general pattern of the temperature/altitude profile, or lapse rate, is constant and measurable by means of instrumented balloon soundings, the temperature behavior provides a useful metric to distinguish atmospheric layers. In this way, Earth's atmosphere can be divided, called atmospheric stratification, into 5 main layers as follows: exosphere, 700 to 10,000 NBSP, km; thermosphere, 80 to 700 NBSP, km; mesosphere, 50 to 80 NBSP, km; stratosphere, 12 to 50 NBSP, km; troposphere, 0 to 12 NBSP, km. A total of 99% of air is in the troposphere and stratosphere. The stratopause at a height of about 50 kilometers separates the stratosphere from the mesosphere, while the mesosphere extends up to 85 kilometers. In this layer, the temperature decreases again, reaching the minimum of about -90 degrees Celsius at the height of about 80 kilometers in the mesopause. Chemicals in the mesosphere are mostly in an excited state, as they absorb energy from the sun. Above the mesopause is the thermosphere that extends up to 700 kilometers. The temperature increases with altitude and can be above 1,200 degrees Celsius at the height of 700 kilometers. The gas is in the form of a fully ionized plasma. For this reason, the layer above the mesopause is also called the ionosphere. The density of air below a height of 150 kilometers is high enough to cause colliding meteoroids to burn into ashes due to friction. It also plays an important role in radio communications, since radio waves are reflected by the ionosphere. Also, auroras occur inside the upper part of the ionosphere. We can say that the thermosphere vanishes into the exosphere at about 700 kilometers, where the air pressure is much lower than you could find in the best laboratory vacuums. As for the mentioned auroras, some of the most spectacular atmospheric phenomena occur thanks to interactions with particles and bodies that are from the outside of the atmosphere itself. Let's see some of them. Airglow, or light emitted by excited atmospheric molecules, is the reason why the night sky is never absolutely dark. Most of the radiation is in the infrared domain, but not only. The same greenish oxygen line is clearly seen in auroras, which are formed at a height of 80 to 300 kilometers. Noctilucent clouds, or night-shining clouds, are tenuous cloud-like phenomena in the upper atmosphere of Earth. No confirmed record of their observation exists before 1885, although they may have been observed a few decades earlier by Thomas Romney Robinson in Armagh. These clouds are thin formations at a height of approximately 80 kilometers, and to be formed they need water vapor, dust, and very low temperatures which are easily attainable in the mesosphere. But water vapor and dust are in short supply. The clouds contain particles, which are less than 1 micron in diameter, tiny crystals of water ice up to 100 nanometers in diameter, and become visible only when the sun, which is below the horizon, illuminates the clouds. They may well come from tiny meteors from space, although dust from volcanoes or man-made pollutants may add to these. Scientists believe that the moisture comes through gaps in the tropopause, or perhaps forms from the chemical reaction of methane and other chemicals. Most favorable conditions to observe noctilucent clouds are at the northern latitudes during the summer nights when the sun is only a few degrees below the horizon. Auroras can be seen mainly from relatively high northern or southern latitudes, where the Earth's magnetic field closes the loop into the magnetic poles. Alaska and northern Scandinavia are the best places to observe auroras, even though they can sometimes be observed up to 40 degrees of latitude when the particles coming from outside the atmosphere are particularly energetic and numerous. Auroras are usually greenish or yellow-green, but red auroras have been observed, as well. They most commonly appear as curved lines with trails and may contain rapidly varying vertical rays. Meteors, also called shooting stars even though they have nothing in common with stars, are the visible passage of a glowing meteoroid, micrometeoroid, comet or asteroid through Earth's atmosphere after being heated to incandescence by collisions with their molecules in the upper atmosphere. They hit the Earth's atmosphere and depending on their mass, mainly, can reach or not the planet's surface. When a meteoroid survives its trip through the atmosphere and hits the ground, it's called a meteorite. Depending on how big this body is, for the majority of the cases, it is reduced into ashes just after 20 or 30 kilometers. From an observer point of view, the duration of a typical meteor event is less than a second and the brightest meteors are called beauties. When a meteorite hits the ground, the consequences can be serious. According to NASA, today we know of about 190 impact craters on Earth. The famous Chicxulub crater on the Yucatan Peninsula, which is 300 kilometers wide, is the result of a very large asteroid impact 65 million years ago, which is thought to have contributed to the extinction of about 75% of marine and land animals on Earth at the time, including the dinosaurs. Van Allen radiation belts is a zone of energetic charged particles, most of which originate from the solar wind, that are captured by and held around a planet by that planet's magnetosphere. Earth has two such belts, and sometimes others may be temporarily created.